Hello everyone, very good morning. So let's start the day one of week 3 of this lecture series. So in last couple of weeks, we learned about the symmetry elements and symmetry operations of any given molecular structure, and we learned how to find out a symmetry element and how to generate the symmetry operations from that particular symmetry element. So in that way, we could find out all the possible symmetry operations of that particular molecular structure. And we also learned about the group, mathematical group, as well as we learned about the molecular point group or symmetry point group, or simply the point group, where the elements consist of the symmetry operations of a given molecular structure. And we learned a few more things, like how to utilize this point group symmetry to find out whether a molecule will be chiral or whether a molecule will be polar in nature, dipolar in nature or not. So what we are going to do this week is as follows. So we will learn a particular technique to combine different symmetry operations, and that is called group multiplication. So we'll learn about group multiplication table as well, and we will also learn a way to find out. Suppose you are given a point group, any point group, for example, like D4D, and then I ask you, okay, tell me what are the symmetry operations that this particular point group contains, that is, what are the elements of this particular point group. So how to do that? That there is a way which is done by using stereographic projection. So we will learn about the stereographic projection, and then we will try to learn how to form a representation of a particular symmetry operation. So like we are calling C3, C4, or sigma, sigma H, S4, all these symmetry operations, how to represent them. Okay, so are there any mathematical framework to do that? Okay, so there is a mathematical framework which utilizes the matrix representations. So we will learn a little bit about the basic matrix algebra, and then we will know we'll learn how we can utilize this matrix algebra to form representations of the symmetry operations, and also we will learn how to take those representations and form the representation of the group as a whole. Okay, so let's get started with the group multiplication. Okay, so we have learned how to combine, or rather we should say that we have seen some of the combinations of symmetry operations in a particular point group. So what we did there, we operated, say we are talking about a binary combination of two symmetry operations. So what we did is we operated two symmetry operations successively on the molecular structure and found out that, okay, what could be the other operation that could lead to this change which one is getting by operating two symmetry operations successively. Okay, so that's how we figured out. Now, if we want to know the exhaustive list of such binary combinations that are possible in a particular point group, in one particular order and also the reverse order, meaning like if I want to find out the binary combination AB, I should be able to know also the result of BA, like we have shown you, like sigma V prime in case of C2V. So we didn't look at what would happen if we would have operated in a reverse way, right? That is sigma V double prime, sigma V prime sigma. Okay. So group multiplication table provides you that particular way to get the exhaustive list of the binary combinations of the symmetry operations. Okay. So when we say here multiplication, that means nothing but the successive operations. Okay. So what you know, so on your screen, if you look at, so if we take a group which has an order h, so if you have a point group which has an order h, you know what is the order? Order is the total number of elements in a group. That means in case of point group, total number of symmetry operations that are there in the point group is the order of the group, which is represented by h here. Okay. So then how many such binary product that we can expect for a group? So the obvious answer will be that it will be h square, which is given here, because h number of symmetry operations will combine with another h number of operations including itself, and then it will give h square number of total products. And here the on your screen, if you look at, you can find out how to do this multiplication. So this multiplication, it can be represented conveniently in the form of a table, right? That we already said. And in that table, it will be a like a square table where you have h number of rows and h number of columns. So what you do essentially is something like this. So for any given point group, say I have a point group, say G. So if I have h number of elements, so I have a trivial E, then suppose I have A2, A3 up to AH. Okay. Then what we do in order to get the group multiplication table is following. So we write also the same symmetry operations, or in general in case of group we write all the elements that are there in this group in the column also in the same order. So we will write E, A2, A3 up to AH. So by now you probably have figured out what are we going to do next. Okay. So we will get h number of rows and h number of columns, right? Each of these units, each of these cells, so by cell I mean this area, each of these cells will contain one product. Okay. And how will be the product? So this multiplied by this. Okay. So you will get the results here, and this as a whole is the group multiplication table. Okay. So we will follow a particular convention here, which is also written on your screen. So the convention is, we take the order as, first we will take the column element and we will multiply it with the row element. So in a sense what I showed you here is, first we will take this and then multiply with this. Similarly we will take this and then multiply with any one of the row elements. Okay. Now at this point there is one theorem called rearrangement theorem, which is important in the context of this group multiplication table. So what does this theorem say? It says that each row and each column in the group multiplication table lists each of the group elements once and only once, and that no two rows and no two columns can be identical. Okay. So the proof of this theorem is pretty simple. You know that if I look at this particular table here, so I will take any particular, say, row of this of this group multiplication table. Say I will take some nth row. Okay, suppose this is my nth row. Okay, so this will be my nth row. So now how will be the multiplications? It will be like here I will have AN, right, as the element. So it will have ANE. Okay. So I will have ANE. I will have then AN2, sorry, ANA2, and so on. So now if you look at all this up to say I have ANAH. Okay. Now this E to AH, all these are unique unique elements of this group, right? So none of these elements are same. That already we have learned. Now their combinations, when I have say like ANE or ANA2, all these combinations are also going to give me different products. Since all the A's are different, so all these products also are going to give me different results. Okay. So in this nth row, I have H new elements are formed by this binary product, which all will be different. Similarly, I can choose any of these rows. Okay. So all of them will be having each different elements that are formed. Now since I am not going to repeat the same binary operation going from one row to another row, that means they also will be different in a sense that all these rows will be completely different. What does it mean? That means what exactly is written here on this rearrangement theorem, that's each row lists each of the group elements once and only once, and that no two rows are identical. Fine. So that is easily visible from this. And same thing can be said about the columns. Okay. I could do the same thing in terms of column also. So this rearrangement theorem holds pretty good. Now let's look at some of these groups. Okay. Group multiplication table. So let's first take the group multiplication table with order 2. Okay. We will term it as G2. Okay. So any order of the group will we'll call it like Gn, okay, for the group multiplication table. So in case of G2, we can see we are using the same approach as I just showed you on the blackboard. So in case of second order 2 group, what are the elements that we have? One is the trivial one, that is identity, and any other element that can be present there. So we are taking that as this element A. So there is only one combination that is possible, because I know that identity combines with any element to give the same element back. So E product E, obviously it is E, and then E product A will give me back A. Okay. So this one also very easily you can figure it out. Okay. Therefore it's really easy to find the group multiplication table for G2. Now let's look at a little higher group, that is group of order 3. So how do we form the group multiplication table for order group of order 3? So let's have a look at here on your screen. So first you write down the all the elements along the row and the column. Okay. Then you start multiplying by following the combination rule that we just stated. So E combines with all the elements and gives you back the same element. So the first row and the first column, that is very easily figured out. Okay. So that is very trivial and one can write it out. Fine. So then we are left out with this region, which will contain 4 different products. So how to go about them? So we can do that only in one way. So now if we suppose choose that that A followed by A is equals to B, or A followed by A equals to E, which means A is its own inverse. Okay. Now, out of these two choices, if we take A, that is A followed by A is identity, then B followed by B also has to be identity. Okay. So that's implied, and if we take that argument and try to follow this one, then we can get up to this, where I have A equals to E, and then B combines to give E. Then I have to fill up this part. Okay. So this two element we are left with choice, where like BA and AB, these two products. So you have to have A here and B here in order to satisfy this row condition, right? Now that will lead you to a problem, because this satisfies the row condition, that is no two elements of this row are same. But when you look at the column side, what do you have? You have the repetition of the product, same element. So you have in the second one you have A twice, while here you have B twice. That is completely disallowed. So that means that we cannot have a condition which is AA equals to E or BB equals to E. Then what are we left with? We left with a condition that is AA equals to B. All right. So instead of having A equals to E, if we choose AA equals to B, then we can end up getting this particular table. And you can do it yourself step by step. Suppose you choose this condition AA equals to B, write it up, and then keep doing the rest of the fill the blanks that are there, and you will end up in this particular multiplication table. Now here, if you look at in this particular multiplication table, you will see no two rows or no two columns are identical. Okay, that's for sure. And in a single column or single row, no two elements are getting repeated. Okay, so this exactly follows the notion of group multiplication table. So this is an unique kind of way to find out the group multiplication table of order 3. In the same way, you can keep going in a higher order, like group of order 4, group of order 5 and 6 and so on. Now in this particular case of G3, we have a pretty interesting thing here to observe. You see, we have chosen AA equals to B. Okay. Now we have first A, then AA equals to B, and then I have A equals to E, right? You can see that easily, because here A is B, so that means I can replace this part by B, so it is essentially AB, and let's see what AB means. So A multiplied by B is E, that's what we have written. So in this particular case, I really do not need to actually look at anything else like B, because this, if I take this element A and then keep operating it, then I will get like A squared, A cube and so on, and that will generate all the elements of this particular group. Okay, so essentially what we have is like A square and A cube, where A cube is nothing but the identity. So this type of group which can be generated, so G3 can be generated by a single element which is A here, right? So A square and A cube equals to E. So this type of particular group which can be generated by one single element, which is known as the group generator, is known as cyclic group. because you can easily figure this out, like you have a, then a square, and then a cube. In this particular case of G3, a cube means e. So a4 means again a square, again a cube. So it's like in a cycle it's going around, right? So it's only a square, and identity. These are the three elements, but this is a group itself, and this is specially called cyclic group. Now some specific things about cyclic group is, for a cyclic group of order n, we just looked at order n equals to 3. So for any general group which is cyclic in nature and has an order n, where essentially this means h equals to n, right? Then x to the power n equals to e, where x is the group generator. We just had an example in terms of this G3, where the generator was a. And this G3 is the simplest example of a cyclic group, and this is a non-trivial example of cyclic groups. Otherwise, one can think of G2 or even G1, if you can say in terms of only element identity. They will satisfy the condition of a cyclic group, but they are trivial, right? So this is the first non-trivial example of cyclic group. This is G3. All right. So now let's look at some of the more concepts here, which is known as subgroup. So what is a subgroup? If you look at it on a screen, a group whose members are all members of another group, both being subjected to the same operations. So what it means is as follows. If I have a group of certain order, say I have a group of order 6. Now out of this 6 elements in that group, if 3 of them forms a group, okay, that is possible. We will see how. Okay, so in that case, this small subset of those elements which satisfies the criteria of forming a group will be a subgroup of the main large group. That is, the group of order 3 which I was talking about will be a subgroup of the main group having an order 6. Okay, and there is a specialty, like this subgroup cannot have any order. Okay, there is certain definite condition for a subgroup to satisfy in order to be called a subgroup, and that is that the order of that subgroup has to be an integral factor of the order of the main group. Okay, that is what is written here. That is, the order of any subgroup G of a group of order H must be integral factors of the order of the group. So in other words, what does it mean? So suppose I have the main group having an order H. So this is the say if I write main group, then if there is a subgroup, its order should be such that, if the order is G, then it should be such that the H by G equals to K, where K is an integer. That's the condition of formation of subgroup G. So what does that mean? That if I have a group of order 6, then the subgroups that can actually be formed will have or can have the order 1, 2 and 3. Out of that, 1 is the trivial example, and 2 will be another one, and third will another subgroup that is possible is having order 3. So here we will look at some of the more some other group multiplication tables, that is G4. So on your screen you have two different sets of this group multiplication table for a group having order 4, that is 1 and here is 2. Now you can see that these two are two different group multiplication table. So you can actually form more than one type of group multiplication tables for certain orders. Okay, so G4 is an example. So we will not be deriving this group multiplication table. So we showed one example with G3, the simplest one, and you should be able to form these two different G4s with that principle that you have already learned. So one thing you can look at here, that from this G4 you can take out a subgroup which has an order 2, and order 2 group will have an unique group multiplication table that we have already seen, that will be a G2. Okay, and you can easily find out the group multiplication table for G2 from this any two G4s. Okay, so now similarly you can find out for what is G5, and you can also find out about G6. So on your screen right now is a group multiplication table for a group which has order 6. We call it a G6, but this is not the unique multiplication table that is possible for a group having order 6. You can form more than this. Okay, another type of group multiplication table, and you should try forming that group multiplication table yourself. Okay, now can we, if suppose I give you this particular group multiplication table, can we compare it with multiplication table for a particular point group which also has an order 6? So what is a group that you can imagine which has an order 6? The easiest option will be C3V. You take ammonia as an example, and if you go through all the symmetry operations that you can have for ammonia, you will find that there are only 6 symmetry operations that are possible: identity, C3, C3 square, sigma V prime, sigma V double prime. Okay, so there are 6 elements in that particular point group. Okay, now can we compare the multiplication tables which is on your screen right now and that with a multiplication table of C3V particularly, that is for ammonia. Okay, so let's have a look at that. Now G6 is again there on the screen, and you have also the group multiplication table for the symmetry operations of ammonia. So what do you see? So here all the multiplications are provided. Now what you should do is to find out what is the similarity between these two, and once you have a close look at both the tables, one for G6 which is an abstract group, and this symmetry point group for C3B, that is ammonia here, you will see that all the rules of a group are obeyed by this group multiplication table for ammonia. So all the symmetry operations here, they follow the principles, which is already something that we already know. Now the most interesting fact here you will find out if you look at the correspondence between the elements that are formed, or the product actually which you form by this group multiplication, and compare each of the table. So you compare the element at row 1 column 1, or say row n column n, and you try to find out what is the similarity there. And what you will see there is that there is an 1-to-1 correspondence between the elements in each of the groups. Okay. For example, you will see that identity is same for both of them, which is not something which we are surprised with. And then essentially the sigma B prime is nothing but A in G6, sigma B double prime is B in G6, sigma B triple prime is C in G6, while C3 and C3 square are T and F respectively in case of G6. And so this is a wonderful thing, that if you can form a generalized group multiplication table, then for any given molecule, you should be able to identify the product of any two symmetry operations once you have figured out what is the corresponding element in the point group multiplication table for that particular molecule. Once you have figured out what is your abstract group for group multiplication table for that same order group. Okay, so we will stop here today, and we will resume from the same point in the following class. Thank you very much.